Alright, so today we'll do a quick summary of flows and cuts. These are topics that I normally do in greater detail, but we've been doing things slowly, so we'll just do them quickly for now. And we'll also do a review, so maybe in the last half an hour of the class. So if you have questions about stuff we've done before, keep those in mind and you can ask. So these could be logistical questions. These could also be things like, I didn't understand a certain thing. So can we go over it? All right. So a couple of announcements. As you all know, the midterm is a couple of days from now, and it will be in class usual time. So please try to come early because we would like to start at about 5 minutes past the actual start of class. So that's that. And also, homework 2 grades were out yesterday night. So yes, I saw that there were a few issues where some people were given late grades even though they had some permission. If you notice anything, just send us email. You can either do a direct message to the TAs plus me on the answer, or you can just write to Vivek, who usually handles all of them. And as you all know, homework 3 is out, and it's due the Wednesday after. Right, so any questions on statistics? Okay, good. All right, so just a couple of things. So last week we did some basic graph algorithms. Okay, so we did Dijkstra's algorithm, which is an algorithm for finding the shortest path between given vertices u and v in a graph. And we said that it is in some sense an imitation of BFS, breadth first search, but for weighted graphs. Right? So if your edges have lengths, then you can do a regular breadth first search, but you can modify it in some natural way, and that's what gives us Dijkstra's algorithm. Okay? And we saw that this can be implemented in time slightly more than breadth first search. There's an extra log n. So that's Dijkstra's algorithm. And we also saw a different algorithm. Actually, we had seen this a while ago, which is a dynamic programming based algorithm called Bellman-Ford algorithm. That's what it's usually called, although it's been, I guess, discovered before as well. Okay. So, and this algorithm has a worse running time, at least in the worst case, right? So it has n times m plus n as opposed to like log n times m plus n. But we said that sometimes Bellman-Ford can be better, right? Like, for example, if there are pretty short paths between your vertices of interest, then this can actually be quite good. Okay. Likewise, if you have some distributed infrastructure, then Bellman Ford can actually be reasonable difference. Okay. All right. So what's the plan for today? So I wanted to cover, say, a little bit about flows and cuts, and there are some interesting connections between these two problems. Okay, and then we'll go on to the midterm review. So how many of you, just to get a sense, know about flows and cuts and graphs? Smaller than number than I thought. How many of you have heard the terms at least? Okay. That's a good thing. Alright, so at least by the end of today you know what they are. Okay, so you may not know the details of that. Alright, so what is so let me define the first problem. It's called the maximum flow in a network. Okay? And you should think of these as communication networks or networks where you ship goods from one place to the other, or you can think of electricity distribution or water distribution, something like this. Okay, so those are the kind of networks we have in mind. And what's the problem? So you have a directed graph. Okay? So you have a set of vertices V, set of edges E, and each edge has some capacity. Okay, so a capacity is something. Think of it like a weight, but it denotes the amount of stuff that can flow on that edge. Okay, so that's the intuitive definition. And you also have two special vertices. One is called the source, and the other is called the sink. Okay, so you write the source as U, sink as V. And what you want to find is the maximum possible rate at which you can send stuff from U to V. Okay, so I'm being very vague here, but so let's look at a concrete example, which is a communication network. So in a communication network, a capacity could be the maximum bandwidth along an edge. Okay? So suppose I have an edge ij, and there is a capacity of 12 here. Then it means that I can send information from I to j with a bandwidth of like 12. I can send like 12 units per second, 12 MB per second, something like that. Okay? So that's what the capacity means. And your goal is you're given the source and the sink, and you want to find the maximum rate at which you can send information from the source to the sink. Okay, so let's see. So what does this mean, right? So in this, let's say you take this graph. Okay, now I could send, for example, I could send 12 units of flow along this path. That's what I will call them units of flow, but it means if you think of it as a network, then I can send 12 packets per second along this path. Right? And I cannot send any more along this path because this path uses an edge with capacity 12. Okay, so that's what I mean by the capacity. But there is some unused capacity here, some unused capacity here. Right? So these edges could potentially carry more information. Okay. So that's one part. And now you could say that okay, I will then, in this example at least, I could for example choose another path. And what is the most I can send along this path? Okay, so just 4 because this path has a edge of capacity 4. Okay, so I cannot send any more along this path at this point. Can I send some more flow in this graph from this vertex to the other? Okay, and how can you do that? Okay, so you observe that there was this other edge of going, other way of going from this vertex to this. So you could say that okay, I will send maybe 7 units of flow along this. Okay, so maybe with a different color. Here I was at 7. Alright? And in this case, I don't think there is any more flow you can send from U2. Okay, so we can reach the optimal flow. And you can interpret the problem in many ways, right? So the way I've said it is, yeah, I'm thinking of it as some kind of a communication graph, and these capacities are like the bandwidths. Some people like to think of it as some flow of water. That's how I guess the name originated. And the capacities of the edges are like, so you have some kind of pipes between these vertices, and it's like the amount of stuff that can fit in the pipe, like the diameter or something like that. Okay, so that's another way in which people think of flows. Okay, so all right. So any questions on the problem itself? Okay. Yeah.
Should we consider only one flow? Like, can we not take 11 from 0 and 0 to 4, and can they be not divided to 7 plus 4? Can we not take two?
Yeah. So I will come. I think what you're asking is, do I have to think of flows as a collection of paths?
Can they divide? Like, if it is water, and like you said, can I take 11 till 0 to 4, and 7 plus 4 be divided and reach all the 11 to 5?
Right. So I claim that those are basically the same thing. Like what we drew here is exactly that, right? So we have 4 going from all the way from here to here, and we have 7 going from here. So that's equivalent to thinking of it as 11 until this point, and then it's splitting off. Okay. Actually, I will come to that in the next slide. Okay. So actually, there are 2 ways you can think of flows. Okay, and I think that's what she's getting at, which is the first thing is you can think of a flow from U to B as a collection of paths from U to B. Okay, so that's what we did in this picture, right? So we said that flow from 0 to 5 is, first I had this path which was of length 12, and then I had this path which was of length 7, and then I had some path which I think did something like this, which is of, okay, this was 4, this was 7. So I thought of it as 3 paths. Okay, one which had a flow of 12, this one had a flow of 4, this one had a flow of 7. So a set of paths, each carrying some flow. Okay. And the constraint here is the natural one, which is that on every edge total flow on that edge is summed over paths that use that edge. Is less than or equal to capacity of E. Okay, so for every edge E, if you look at the total flow over paths that use that edge, then it must be smaller than or equal to the capacity. So in this example, for instance, if I looked at the edge 20, okay, there were 2 paths that use that edge, right? So one is this path, and the other is this path. Okay. And those 2 guys must have flow values, like here there was flow of 12, here there was flow of 7. Those 2 must sum up less than the capacity of the edge, which is 20. Okay. So that's the constraint. that you do. Okay, so at least if you view flows as a collection of flow paths. Okay. So the problem statement here. Okay, so this, at least for me, this is the simplest view of flow. So these are just, you want to send some information from U to V, think of it as going along multiple paths. And along for each path, you have some flow value that you send. And you have capacity constraints. That just translates to on every edge, look at all the paths that use that edge. And flow values on those paths must add up to something smaller than the capacity. So this is a very simple way to view flow. You can also view flows in an equivalent way as just flow values on edges. So now the first definition is natural, but it's also a bit cumbersome to work with, right? Because now to describe a flow, you've got to tell me, oh, here's one path, here's the second path, and so on. So this is somewhat cumbersome to tell you what a flow is, right? So the second definition is much cleaner. So it just tells you on every edge how much flow, how much information is flowing, okay, and in which direction. Okay, all edges are directed, so direction is implicitly there. So it tells you. So this is just flow on edges. So this just views of flow. As a function from edges, from the set of edges to non-negative reals. Okay, so this just means that for every E, have the value F. Now, this is simple, but you know, this is not all values Fe that I come up with can correspond to flows, right? So what are natural constraints you can think of here? Okay. So this view is just saying that, for instance, in this graph, I would like to write a function where here I will write 12 because 12 is the total flow on that edge, and here I would write 11, here I would write 11, here I would write 0, and so on. Okay, so that's the Fe value I'm associating with this. Okay. Now, if I were to just define the flows using these Fe values, then what are the constraints that Fe must satisfy, that these numbers Fe must satisfy? Yeah, Fe, okay.
The flow into an outer reach node must be the same.
Right, so the more obvious one is the capacity, right? So which is that Fe must be less than equal to capacity of E. So that's an easy one. The next one is what she's saying, which is that if it really is a flow, right, then for any node that is not the source or the sink, you must have the flow going into that edge, into that node, is the same as the flow going. Okay? Because a flow is, technically speaking, it's composed of paths, and in a path, anything that goes into a vertex that's not the start of the path also has to leave you. So, for all vertices, so this is one constraint. Second constraint is for all vertices W not equal to U comma V, total flow into W equals total flow out. Okay. So what does this mean? So if I take some value, some vertex W, and let's say there are some edges E1, E2 coming in, and E3, E4 going out. Okay. If I had something like this, then F E1 plus F E2 must be equal to F E3 plus F. Okay. So these are called capacity constraints, and these are called flow conservation constraints. So, conservation. This is conservation in the physics sense of the word, right? Which is that something is maintained constant. Yeah.
Can FE3 and FE4 be less than the left-hand side? Like, for example, when we went through like the second time?
Oh, you mean it can they be less than the capacity? Or
like, can the outflow be less than the inflow?
no, so unless you are the sink, right? So unless you are the sink. If it's a sink, then nothing goes out. Right? But otherwise, they have to be exactly equal because were you talking about this vortex?
Yeah, sure. So vertex 4.
So for vertex 4, there's 11 amount of flow that comes in, and there is 7 plus 4 going out. Right? So it's the same as.
Okay, so what about vertex 1 when 16 goes in? Oh, you say only 12 goes in?
Right, so that's the point. So if you have if you take vertex 1, you can't have 16 going in. Yeah. Right, and these two notions of flow, these two definitions of flow are both equivalent. So you can either think of a flow as a set of paths, each having some flow value, and it satisfies that constraint. Or you can just think of a flow as being defined by just some function on the edges, where you map every edge to some flow value for that edge, and these values must satisfy these two constraints, okay, the capacity and the conservation. So it's actually a fairly simple exercise for you guys to see how these two definitions are equivalent. In fact, going from paths to flow values is basically trivial, right? Because if you had a collection of paths, if you wanted a flow value, you just sum up all the flow that uses that edge, and that gives you a way of going from one direction to the other. Going from flow values to a set of paths is a little bit more tricky, but even that is somewhat easy to do if you think about it a little bit, right? So you know that things are conserved, so if you get to start off at the source, you start building paths. Yeah, I mean, you can prove easily that you will never get stuck unless you actually used all of it. Okay, so I won't go into why these two are equivalent, but it turns out these two are equivalent formulations. Okay. So any questions on the two definitions? All right. So this is here, then we go on to okay, I don't know what happened. If you open this. So this is an updated version of iOS, so some things might crash, but they will come back hopefully. Okay, so all right. So these are definitions of flow. So now let's see why. Yeah, and in right, at least defined like this, you can define the max flow problem formally as well, right? So you can say that in the first definition, it's like you want to maximize the sum of the flow values on all the paths that you choose. Okay. And in the second definition, you can define it as you maximize the flow that goes out of the source. So those are how you would formally state the max flow problem. Alright, so now let's look at a simple greedy procedure for max flow. So what would, inspired by what we did before, so if you had a graph like this, how would you find the maximum flow? What would be a greedy procedure that you might follow?
Take the max edge out of
Take the max edge. Interesting. Okay, so let's start with U and V. Right? So you want to take the largest edge, okay, and then what?
take the max possible edge at the maximum.
So that's something here, okay, and continue. So you reach. So one issue you face either way is that you may not get anywhere close to V, right? Like the max edges may never lead you to V if you just were to do this, right? I mean, this graph is simple, so you are lucky, but you could have a case in which the max edge leads you to nowhere, right? So still an interesting thought, right? It says you want to send the most amount of flow, so try to send the most you can. Yeah.
Can you do it going backwards? Starting from
Right. So, but what is different, right? These are symmetric in some sense. Like you would encounter still a similar problem.
I mean, wouldn't it guarantee you get back to you at the very least or not?
Now, if you only start from V, then it's the same as starting from U, right? Because it's doing the reverse thing. But now you may never get to U. Yeah?
And maybe you could start at U and just assume that you'll be able to use all capacity. So like coming out of U, there's 20 plus 10.
Okay.
Say, I'll just send some information through all of it. And then you go to the next level, like all of U's neighbors.
Mm-hmm.
And then just start putting constraints on it. Say like, well, the next node gets 20, and maybe it can or maybe it can't use all of that. And if it can, you just, I guess, distribute it. I didn't get that part. I'm not sure how you distribute it on the next level. Like you could start with that.
Yeah, so I guess what he's suggesting is, the second definition, right? Like, hope for the best. Just try to send in flow as much as you can, and hope that the network kind of pushes it around, and hope that you end up with something good, right? So it's a natural thought. Yeah. Okay.
So what if we take a shortest path from U to V, which we can do.
Okay.
Then when we have an edge that is at full capacity, we remove it from the graph and find a new shortest path, and repeat until there's no more paths.
Okay, so what he's suggesting is a slightly different procedure. So it's overcoming two of the issues, actually issues that both of you had, right? Which is, you were trying to go for a greedy thing where you push as much flow as possible along one edge. And his thing was similar, except that he was trying to push along all edges and trying to go to the place. But both of these had one problem, which is that flow that started off at U was not guaranteed to reach V. Okay, and it was explicit in his example and a little bit more subtle in his argument. But the one he's suggesting is, don't have this problem. Maybe you won't get too much flow, but at least get the paths right. Okay, so what he's saying is, take some paths from U to V and send as much flow as you can from along this path until some edge gets saturated. Okay, so I would view this as going by the first definition of flow, right? So while what these guys are proposing is more like the second definition of flow, where you view the flow values as some numbers on every edge. Okay, so it's an interesting distinction. So you should So right, so what he's suggesting is take the shortest path, and you would then put a flow of 10 along this path because you cannot have more than 10. And right, and now you see if there is another path from U to V. So, right, so now the question arises, so in this case there is another path. Okay, so let's do this thing here. And now you have only 10. And now, is there a path or is there not a path? Yeah, so you should not view these as like using edges. You should just view this as, oh, okay, this edge still has a capacity left. So there is 10 left here, and there is 10 left here. And you look at the shortest path in this graph. Okay, where you now have 10, 30. It's just that these two edges are gone because these have reached full capacity. So, and now you can hope to send 10 units of flow along this green path. Alright, so, and this procedure is as find from U to V, put as much flow, send as much flow as possible. Update capacities on edges, i.e. keep only the remaining. Okay, and then you repeat. So this is a procedure which at least always finds a valid flow from U to V. It may not be the optimal flow, at least we don't know, but it at least finds a valid flow from U to V. So it does not have the issues that the other solutions had, which is that you may send some stuff out of V never to, U, which may potentially never reach V. Okay. So it overcomes those problems. But it may not be optimal in the sense that it may find some flow and there may be, the algorithm may be stuck. But, alright, when does the algorithm end? It ends when there is no path from U to V. Okay. So this is an algorithm that at least finds a feasible flow. So the algorithm. Right? So now the question is something like this optimal, right? So what do you guys think? You always find the shortest path that you try to send as much flow as possible. Would you reach the
Yeah. I don't see why you have to find the shortest path. Does that matter? If you just find any path?
right? So yeah, so that's a good question. So find shortest path is yeah. So you don't really need shortest. You can find any path. In fact, I was kind of hoping that people would say find any path because the next picture I have a counterexample for that. But for shortest path, actually, I did not draw a counterexample. But anyway, so it turns out neither of these algorithms actually end up in an optimal solution all the time. Okay, but yeah, like you were saying, you don't. There was nothing very sacred about the shortest path. You could have found any path and updated stuff along that. Yeah, and generally it turns out that the choice of path matters. Like in this case, if you, in fact, I was suspecting people would say find a path that would take the most, that would allow the most amount of flow. Okay, and so in this case, that would be something that like sends 20 along this path. Okay, so suppose you ended up with, you started off by sending 20 units of flow from U to V. Okay, the long lines of what he suggested. Okay. Then now you immediately get stuck because now there is no path from U to V. Okay. So this is so in the previous solution you ended up sending 10 plus 10 plus 10 equals 30 units of flow. Okay. But if you chose this path to start with, you send 20 units of flow in the first iteration and then you get stuck. Okay, because once you chose this, there is no way of going from U to V anymore. There are no paths. So, do you guys see this example? Okay. So what this suggests is that maybe shortest paths are nicer in some sense, but they're not always nice. You can actually come up with examples where even the shortest paths get stuck in something that's not optimal. Yeah, let me think of an example.
Maybe you could increase 20 by 40.
Which 20 by 40?
The last one, 10, 20.
You mean this one?
Yes. In the existing part gives you 50, but the shortest part give you 20 for the count.
No, the largest is still 13, right? 13. Yeah. So yeah, I mean, I'm sure you can come up with. Maybe I will add one in the notes or something. Yeah.
If you remove the top right edge,
Yeah.
then the shortest path is no longer optimal.
Oh right. Okay. Yeah, that's a great example. So what he's saying is, if you just looked at the same graph, but you just remove this edge. Okay. So you just have 20 here, 30 here. Yeah. Okay. So if you looked at this is still fine, right? So this is still fine. So because you'll still find the second path. But let's see.
What if you make the top right and you increase it so it becomes 50?
increase it further.
Yeah. So it's no longer the shortest, the top path from 20 and 10. You increase the 10 so that it's no longer shortest. Then you would still have to take 20, 30, 20 path.
Yeah, so that's what I was going to get at. Like these lengths are not very sacred because you can always throw in more edges, more vertices in the middle. Okay, and you can make these 10, 10, 10, and now the shortest path, and actually do the same with this guy. Okay, so if I make these, okay, so this is an artificial example, but you know, in this case, the shortest path in terms of number of hops is the middle one. Okay, so yeah, so what this example says is that there's nothing very special about short paths.
What if you choose pass with the lowest capacity?
Sorry?
What if you choose pass with the lowest capacity? Maximum capacity.
Oh, so again, I'm sure you can come up with a counterexample. Okay, so yeah, okay.
Is this algorithm arbitrarily bad, or can we show that there's some kind of pattern?
Yeah, so that's a good question. I'm not sure actually. I would suspect that this is quite bad, but I haven't thought about it. That's a good question. Actually, this is the kind of question you should be asking, because this is what we have been asking in different parts of the class, right? We've been asking, oh, can this algorithm be arbitrarily bad? So, again, I think this is a good homework question. Yeah, very good. So, yeah, my guess is that this can be arbitrarily bad, because you can you could have some very heavyweight edge that gets used by lots of small bats, and you could potentially make it quite bad, I think. Okay, but yeah, it's a good thing for you guys to come up with examples where this is quite bad. Okay, so this is nice, right? So we have a whole bunch of so we had a bunch of interesting comments. Okay. All right, so this is so these kind of algorithms have certain issues, and now so the idea behind this Ford-Fulkerson algorithm, which we won't get into, but I just want to describe the main idea, is it provides a nice way to correct for mistakes that we've made. Okay, so that's how I think of this algorithm. So it turns out that this problem actually can be solved efficiently in polynomial time. Okay, so you can actually find the best, the maximum flow from U to V. And the algorithm for this is to do something very similar to what we've been doing, which is find paths and route flow along the paths. Except that you have some kind of a means, some formal means to push back on flow that you've already committed to. Okay, so in this example, for instance, let's say I have committed to like 20 units of flow along, I have sent 20 units of flow along this. Now I know that I'm stuck, right? So now I know that if I take this, then I'm stuck and so on. But what if now you realize that I can take a 10 here and maybe reduce flow on this a little bit and then use that edge perhaps. Okay. So that's kind of the idea behind this Ford-Fulkerson algorithm. Okay. So it gives a formal way to correct for mistakes that you may have made. Okay. So unfortunately we don't have time to cover this algorithm, but you will find it easily online. Okay, so it's one of the few examples where you can think of it as some kind of backtracking, but you can actually make it work. Okay, so it's so you can correct for mistakes. You can actually prove that it works very well. Okay, so yeah, as I was saying, we won't get into this algorithm, but that's the rough idea of that. All right. So now let's move on to a different problem, okay, which is defined as follows. So it's structurally somewhat similar. Okay, so it's you're given a directed graph VE. Again, you're given some directed graph, and each edge has some cost. So edges have some cost, and you again have some source and you have some sink UV, and you want to find the smallest number of edges to cut. Okay, the smallest, yeah. So what I mean by this is min in terms of total weight. So min weight, min total cost. Set of edges to cut, so that there is no remaining path from U to V. Okay, and as you can imagine, I mean, people studied this problem in the 40s when they were during World War II. They were trying to see how you can cut off supplies to certain cities and stuff like this. And so there is some price to pay for cutting different roads or bridges or something like this. And which ones do you choose so that you have least risk and you still are able to disconnect things, right? So this had some real applications even back in the day. Okay, so but yeah, but of course people nowadays use it for lots of much nicer applications like image segmentation and so on. Okay, so this problem is very useful in lots of settings. But the problem is just this very simple one, that you are given this directed graph U to V, and if I had some graph that looked like this, okay, and let's suppose all edge weights are 1. Then I have to cut at least two edges if I have to disconnect U from V, because I mean, you can see that. But if instead I had some graph that looked like this, the V is over here. Okay. Now it's enough to just cut this one edge. Yeah, or in general, you could have something where you have some bottleneck edge, let's say. Then it's easy to disconnect U from V. Right. So then, if you had a graph like this, all you had to do is cut something off. So yeah, the reason I drew this picture is that I didn't want you guys to get the impression that you always cut things connected to V. Okay. Sometimes it may be better to cut something in the middle. So, all right. So is the problem clear? Okay. So this is a somewhat natural problem. Okay. So again, if you go back to this example, you can see that there's nothing really better that you can do. Or if you cut, let's say, only this edge, then there is still some path. So you have to cut both of these edges. You could also do some more expensive cutting where you will be cutting this edge is very pointless because you still have to cut lots of edges. And yeah, so here it turns out that the min cut value equals 30. It's the sum of all the edges that you need to cut. This is how you define the value of the minimum cut. Alright. So actually, yeah. So now how are cuts related to flows? Right? So it turns out here's a somewhat simple theorem, but something that I would like to mention, which is, so suppose you have a weighted directed graph. So you have some directed graph and you have edge weights, and let's say you have some vertices U and V. So you have some U and you have V. Have some weighted directed graph. weights are some 2, 4, whatever. Okay. So you have some edge weights. Right? So I'd like you to do two things. Okay, so first interpret this as a flow network where the edge weights are actually the capacities of the edges. And let's say you find the maximum flow between U and V. Or you find some flow between U and V, and let's say that the value of that flow is F. So F is value some flow from U to V. When you interpret this, when you interpret the weights as capacity. And next thing is you interpret this as the weights as costs, okay, for the min cut problem, and you find some cut which is some set of vertices, some set of edges, removing which disconnects U from V. Okay. So if you remove those set of edges, there's no way of going from U to V. So and let C be something like that. C is value of some cut, i.e. Actually, one thing that maybe I didn't clarify as much is the cut problem also is defined on directed graphs. Okay? And we would like to remove edges so that there is no path going from U to V. Okay? So there may still be paths going back from V to U. So that we don't care about. So this is, in undirected graphs, these two are the same. Like a cut from U to V will also be a cut from V to V, but in directed graphs these could in general be different. Okay. So that's why I always write things like disconnects V from U. Okay, so it just means that after you remove these edges, there is no path from U to V. All right. So F is some flow from U to V, and C is value of some UV cut. And what I would like to claim is that F is less than or equal to C. Okay, that's the theorem. Okay. That any cut gives you an upper bound on the value of any flow. Okay. So that's what this theorem says. So do you guys understand the statement?
Question?
Yeah.
So is a cut always pertaining to like one vertex?
No. Yeah. So that's a good. Yeah, like in this example, I said that removing this edge, okay, disconnects U from V. But I am not removing all the edges out of this vertex. Right? So this vertex could have had edges that went into this part. So yeah, that's a good point. So cut is just a set of edges. So a cut is they need not correspond to like a single vertex or anything like that. Yeah, in this example, presumably this and this is also a cut, and yeah. It's not the minimum cut because there was a slightly better one, but this is still a valid cut. Alright. So any other questions? So I'd like to claim that you can't have a flow which is more than a cut. Okay, and I'd like to claim that this is actually intuitively a simple statement to see. Okay, so can you guys think of an intuition as to, suppose I tell you, let's say you have an unweighted graph, like all edges have weight 1. Now, a flow is just a collection of edge disjoint paths, right? So actually, so think of all edge weights as 1. Okay. At least in this example, what is a flow? We said that a flow is a collection of paths So here are 2 paths. But if all edge weights are exactly 1, then these paths cannot share edges. They can share vertices, like I drew here. They cannot share edges, because then the total flow on an edge would actually be 2. Okay. So any flow is just a collection of edge disjoint paths. Okay. And now a cut, as before, a cut is just simply subset of edges whose removal disconnects V from. So this is in the graph, it is some set of edges, right? So let's say I take some edge like this edge. Okay, so I have a couple of edges, let's say. Their removal disconnects V from V. I would like to claim that the number of edges, that the maximum, that the flow I can have is always less than or equal to this. Okay. So can you guys see how one can prove something? Yeah?
Well, you can't take away more edges than you have flows. If you take in the last flow edge, which would be the sum of, which would be F, you can't exceed that. You've taken all the edges off from the flows. So you cut all the edges, the set of C is F.
Right, I think you have the right idea, but I'm not sure if you're phrasing it correctly.
Probably.
Okay. So the easier way to think about it is, look at any cut, okay, and let's say I remove all the edges in the cut. Okay. Now, by the definition of a cut, there cannot be any path going now from U to V. Okay. So at this point, the maximum flow from U to V is actually 0. Okay. And now you look at the original flow, and you see, you look at each path in that flow. Now, you know, the original flow was using, maybe it was using some of the edges in there, so it consisted of a bunch of paths. So let's call them F1, F2 up to some Fp. Now, so each of them is some flow value, and F1 plus F2 up to Ft is actually the value of that flow. These paths can share edges, it's just that I have nicely drawn them so that they don't share. Okay, so but in this example, they don't share they don't share edges. Okay, so that's why this is nice. So this is a simple case to think about. Okay, so they can share vertices, but they don't share edges. So now the cut edges, right? So I can't have a path without any cut edge, right? Because if there was a path without any cut edges, then even after removing all those cut edges, that path would have survived. Okay? And that violates the definition of a cut, right? A set of I defined a cut as a set of edges whose removal disconnects B from U. Okay, so if I remove those edges, there is no path from U. So what this means is that each of these paths at least has one of the cut edges. So some of the paths may have two of them, that's fine. But I'm just saying that each path has at least one. Okay? So the number of paths you can have is smaller than or equal to the number of edges in the cut. Okay? So any questions on that? Yeah.
So, okay, so this property holds true for like an entire graph, and when you're looking at all flows within a graph, not one flow in particular, or does it also hold true for just one?
So give me 1 second while this charges. But yeah, so what I'm saying is actually true for any flow, right? So take any flow. Okay, it consists of a bunch of flow paths. I have simplified the problem so that all edge weights are 1. Okay? So a flow is basically a set of edge disjoint paths. Now the value of the flow is the number of such paths, because every flow path has value 1. Okay? And I would like to claim that the number of paths is smaller than or equal to the size of the cut, right? And I'm showing that by saying, look at any path. It must have at least one of the cut edges. Okay? And so that's that. So let me write this. So any okay, and this implies that number of paths must be less than equal to number of edges. Because these are edge disjoint paths. These paths don't share it. So yeah, so this is a simple setting, but I think this setting illustrates the main idea behind this thing. So it's yeah, so I'll pause here because yeah, so this is mostly what I had to say about flows and cuts. That this is a this is a nice theorem. So it's at least in this unweighted case where all weights are 1, this is the statement is very keen to see. So does anyone want me to go over this again? No? Okay. Oh.
So the definition of a cut, you mean we have to add all the weights of the edge we have cut?
Yes. So the value of a cut is the sum of the weights of the cut.
Flow using those cuts, and suppose we cut to 10 and 20, so the value of cut is 30, not the flow use the cuts.
Yeah, so the way I've defined the problems have nothing to do with one another, right? So a cut is just set of edges whose removal disconnects V from U. Leaves no path from U to V. Okay. And the value of the cut is the sum of the weight implied distribution. And in this case, all edge weights are 1, so it's just the number of edges that you've chosen. Yeah.
Is it that the definition mean is it just from U to V or is it from U to V and V to V?
Only from U to V. So if you remove the edges of the cut, then there should be no path from U to V. There could still be some paths from V to U. Yeah. Yeah. Yeah.
If they're all edge weighted at 1, why would the number of paths be less than the number of connected?
Oh, because it could be that one of these paths had actually two of the cut edges. Okay, those would still be a set of cut edges because if you remove those, there is no path. Yeah, yeah, but that's a good question. Yeah, so you could, in principle, have this to be smaller. All right. So what is nice is that what that this says that any value of any flow is smaller than or equal to the value of any cut. Okay. So that's what the previous claim shows. And so in particular, you also have that value of max flow is smaller than or equal to value of the min cut. Okay. So it's like saying if I take any flow, it has some value. It's smaller than or equal to the value of a cut. If I take some other flow, maybe it has value here, but it's something. So what we have shown in the previous slide is that value of any flow you can have is smaller than or equal to the value of any cut. So in particular, even if I took the best possible flow, okay, that is one that has the largest possible value, will still be smaller than or equal to the value of the minimum cut, which is like the worst possible or like the smallest possible cut. So that's what this statement establishes, right? So this is actually a strong statement. The value of any flow is this. Okay. Now it turns out that the proof of the Ford-Fulkerson algorithm is actually quite unlike any proof of correctness you've seen. So remember, the Ford-Fulkerson algorithm is an algorithm for the max flow problem. And the way you prove the correctness of that algorithm is by exhibiting a cut whose value is actually equal to the value of the flow it produces. Okay, so this is a subtle thing. So if you don't get it, I mean, you can read the notes, but it's a nice point. It is that yeah. So the proof goes by saying proof of so this is proof of correctness. I haven't shown you the algorithm, so there is not that much point in saying too much about this. But it's a nice idea. It's unlike any correctness proof that you've seen. That's why I would like to mention. So it says it exhibits a cut whose value is equal to the value of the flow produced. Okay. So as part of the algorithm, it also gives you a cut, and the cut has value equal to the value of the flow that it produces. Okay. And this automatically implies that the flow is the optimum, is the best possible flow, is the maximum flow. Right? Because there is a cut. So it's like saying I give you a flow and I give you a cut with the same value. Okay? Then it must be that this flow is actually the max flow and this cut is actually the minimum cut. Right? Because I know that the value of any flow is smaller than or equal to the value of any cut. That's the very cool thing about the proof of this Ford-Fulkerson algorithm. Okay, so it exhibits a cut. Okay. And it also is nice because it also tells you that these values are in general always equal. Okay. Because the algorithm finds some flow where the value is equal. So anyway, so this is, yeah, since we are slowly running out of time for the review, yeah.
Does there always exist a flow which had minimum cut?
Yeah, whose value is equal to the cut, right? So it exists, and the reason it exists is by this Ford-Fulkerson algorithm. Okay, so it turns out that the algorithm terminates with some flow, where it can also exhibit a cut whose value is equal to the value of that flow. Okay, and I haven't told you the algorithm, so so that's why you want to be why that is true. But this is a nice fact, and this is so this is called the max flow min cut theorem. So in general, in any graph, max flow is equal to the min cut. So this is the picture you got to remember. Okay, so like flows are things that are on the left. If you take any flow, it's less than or equal to the value of any cut. Okay, but there exists some flow which is equal to the cut, and that is like the max flow, and that's also equal to the min cut. So, all right, and this is called the max flow min cut theorem, or also the Ford-Fulkerson theorem. Yeah, and it has a bunch of applications. Maybe we will not get into those. But actually, one nice application of this theorem that I would like to mention is that we really don't know of good algorithms for cut independent of flow. Okay, so if I ask, I mean, like the min cut is a natural problem, right? I gave you some motivations, like, and so it's a natural question. But the only algorithms we know, at least in terms of exact algorithms, at least okay, now we know others, but many of the algorithms for cut actually go via the problem of flow, which is think about it, it's a subtle thing, right? You have this cut problem that you could define independently of everything else, and you know the algorithms for this problem go through algorithms for a totally different problem. This is the problem of flows. And this is, conceptually a nice thing. Okay. All right. So that's one good application of this. All right. So this is all I had to say. New stuff. We don't have too much time left, but I guess we have office hours. So I just wanted to say that okay, these are like the things we'll have for the midterm, and. So most of the things have been, so these two you've done them in homeworks 1 and 2. And this, we haven't really done basics of graph, but these are the two things that we did in homework 3. So that's why I look at the homeworks just to get a sense. Midterm will be easier than the homework, or in general all exams will be easier than homeworks because you have only a finite amount of time. Okay. So that's the. Any questions you have?
Are you going to end up posting the solutions for the finals that you gave us for the examples?
Oh, I could do that if you want. So would that be helpful? Okay. So can you post on Piazza so that I remember? Okay. So any questions? Yeah?
Question about dynamic programming. Mostly I just want to make sure that I'm understanding this correctly, but in general, if we're trying to figure out the running time of a dynamic programming problem, it primarily just boils down to the number of subproblems, right? Assuming the subproblems can be run in constant time.
If so, yes, Usually the subproblems themselves take some time. Like in your in this cake cutting example from homework 2, subproblem were taking something like k time because you were checking all possible things, right? So usually it is some optimization over things. Okay, like in the tree problem, if you remember, the subproblem takes. So each problem takes time that is proportional to, I guess, the number of descendants or the number of grandchildren it has, or something like that. Actually, if you are not careful and if you only had grandchildren, the runtime analysis would be a little bit worse. Okay, so I think the TA's got that wrong. The TA's got it slightly off for the tree problem. I don't think you mentioned for one of them, but yeah. Anyway. So, all right. So that's yeah. But in general, dynamic programming, what you said is correct. Okay, like so there's one aspect there, which is that sometimes you may not end up solving all the subproblems. Like there could be lots of subproblems, but you don't ever encounter a few of them. But you know, in that case, maybe doing dynamic programming the way we've been doing it is not a great thing, because you anyway store the answers to all possible subproblems. Like some of the answers may never be looked up, in which case you could avoid computing. But we haven't really looked. Yeah.
We can bring anything. Is that right?
So yeah, you can bring anything printed. You can download anything. You're just not allowed to use the internet during the exam. Okay. And of course you will sign an on record and there will be TA. Okay, so this is not very super strongly enforced, but there will be TAs going around, so you're obviously doing something there. Right, in general, my thing is that the questions will be relatively easy, but they will test if you've understood the material. And somebody was also asking how much you have to go into the formal proofs in the exam, and that's a good question. Usually, I will ask you to only write like a couple of sentences of justification. Okay? Try to write a compact thing, because I mean, the exam is just an hour or so.
Yeah. I do have a question on how much, like, when we do time complexity analysis, if we have, you know, some recursion or something, will we need to solve that out?
Yeah, so if the problem asks you to do it, you should do it. If it doesn't specifically ask you to do it, you don't have to care about it.
So do you expect that there will be a lot of that on there, or?
No, I will. If I need anything, I will ask for it. Okay, so in terms of writing down proofs, because I don't want you guys to spend your time writing out long proofs. Okay, so if I specifically give you a recurrence and ask you to find a closed form, then you have to show the steps involved. Okay, and I will also mention that show all the steps involved. Okay, so it will not be ambiguous. Yeah. All right, good. So